Hi, everyone. Thank you so much for joining us for our fourth webinar in our series, AI Applications in Earth System and Climate Science, hosted by NOAA's Climate Program Office and the NOAA Center for Artificial Intelligence. This session will highlight research on topics of climate variability and climate and weather extremes. The idea for this series is to feature new applications of AI and machine learning tools in research from NOAA scientists and NOAA-supported investigators. This series will be a way to share ideas and connect with others in the field. We hope to showcase innovation and share cutting-edge applications of AI and machine learning that help us understand and address complex challenges. We're also aiming to work toward answering some overarching questions in these webinars, like how is AI being leveraged as a tool in research, and how are important partnerships across NOAA, the academic community, and private industry driving advancements in AI and Earth and climate science research. We really do want to emphasize our collaborations. Our NOAA scientists and programs have strong partnerships across disciplines in academia and across agencies and other institutions, and we're really excited to showcase that. So to start off, I'd like to introduce the speakers for our first presentation, and I'm going to make Andrea the presenter now. So our first presentation will have Andrea Lopez-Lang as she's an associate professor in atmospheric and ocean sciences at the University of Wisconsin-Madison. Today she'll be presenting alongside PhD candidate Elena Fernandez, who is at SUNY Albany in atmospheric sciences. So among other work in their research portfolio, Andrea and Elena have done a lot of work on a project geared toward assessing dynamics in the lower stratosphere and their influence in extreme events during North American winters. This project was supported by a joint initiative in the NOAA Climate Program Office to understand the causes and mechanisms of extreme climate events. So this was through the Modeling, Analysis, Predictions, and Projections, or MAP program, the Climate Variability and Predictability, or CVP program, and the Climate Observations and Monitoring, or COM program. So thank you so much, Andrea and Elena, for being here, and take it away.
Thanks. So the way that this is going to work is I'll do a little bit of an introduction, but really I want to highlight some of what Elena has been working on. And so you did a great job. Thank you so much for introducing our work with the Climate Program Office and some of the work that we've been doing. But what we're going to be talking about today is really taking some of that work and looking forward to a project that Elena will be continuing to work on. She was recently awarded a UCAR NOAA Wings dissertation fellowship. So this will be some of the work that she is sort of carrying on as she moves on to finish her dissertation. So we'll be thinking about steps towards using metrics of stratospheric variability. And a lot of these metrics came from our recent NOAA award for thinking about tropospheric temperature forecasts and how we can use information that's happening or about the variability in the stratosphere to really motivate identifying what are the key features or components of stratospheric variability that we need to think about to really enhance our temperature forecasts, specifically at subseasonal timescales. So about subseasonal forecasting, I'm sure many of you have heard a lot about subseasonal forecasting. And the way to think about subseasonal forecasting is that the climatological forecast is not that great. We don't have very good skill for any random day in a subseasonal forecast. But there's periods of time when we have increased predictability because there's things happening in the atmosphere or the ocean system that increase the predictability of that subseasonal period. And so this is a figure that really captures some of the sources of predictability on that subseasonal timescale. And so there's a variety of different phenomena that vary slower than climate, slower than a traditional weather timescale, but faster than a climate variability. And so these include things like ENSO, these include things like land surface memory, convection in the tropics, from the Madden-Julian oscillation. But the thing that we really want to highlight here in our work is thinking about the variability from the stratospheric polar vortex. And so the stratospheric polar vortex is a feature in the atmosphere that develops every winter season, and the variability and the strength and the location of the vortex can enhance or be a source of predictability at these subseasonal timescales. So anomalous stratospheric conditions, so anomalous with respect to climatology, can modulate the tropospheric flow. And a hand-wavy way to think about it is really thinking about that the stratospheric polar vortex is sort of the top boundary of the tropospheric weather that we experience in the wintertime. So if we have anomalous conditions, they can extend the predictability beyond the medium range because we have this sort of anomalous top condition to thinking about our weather. So if we're trying to understand the polar vortex, many of you are probably very familiar with thinking about the polar vortex in the sense that we have a very strong circumpolar westerly circulation when we have strong vortex conditions. And this westerly circumpolar circulation in the stratosphere is located between about 10 and 30 kilometers above Earth's surface, or 10 and 50 kilometers, so 10 to 30 miles above the surface. And the polar vortex really consists of two parts. There's the temperature component, where the cold air is really within the vortex itself, and we have warmer air outside of the vortex. So that's the thermal component of the polar vortex. But we also have that westerly circumpolar circulation that is the momentum component of the vortex. And so this vortex that consists of a cold polar region and the westerly winds around that cold polar region, when it's stable, it's located directly over the polar regions, and it can have manifestations in the troposphere, and we can see those manifestations in the structure of the tropopause, or the polar jet stream. So we have a stable polar vortex over the pole. We have a pretty westerly jet, a lot of zonal components to the flow of that westerly jet. But when we have a disturbed polar vortex, that cold polar region with the westerly winds around it can be deformed or stretched. And when that happens, the polar jet at the tropopause level becomes more meridional. It becomes wavier. And it's when this polar jet becomes wavier that we can start to see the high impact weather, or the extreme weather in the troposphere. And so associated with this extreme weather, we can have cold air leave the Arctic and produce cold air outbreaks. We can have warm air moving north. And a lot of times during disturbed polar vortex conditions, we have really anomalously warm Arctic surface temperatures. And this is really important when we're thinking about subseasonal prediction, because we can have increased predictability of extreme events in the troposphere. So the way that we get the disturbed polar vortex is really by thinking about the dynamics that allow the tropopause jet to communicate with the stratospheric polar vortex. And this figure that I've put together all the way on the right of your screen is really representing this coupling. And so we have, this is a vertical cross section going from the equator to the North Pole. That dashed line in the lower part of the figure represents the tropopause, the dynamic tropopause, where the tropopause slopes in the mid-latitudes between the subtropics and the polar regions is where we have our tropopause jet. And it's via wave activity flux communicated between the tropopause jet and the stratospheric polar vortex that we really get this coupling between what's happening in the stratosphere and what's happening in the troposphere. So we can have increased wave activity where this weakens the vortex in the stratosphere. We can have decreased wave activity where we tend to have more strengthened polar vortex conditions. And so a lot of times we measure the strength of the polar vortex based on that circumpolar flow, the strength of that circumpolar flow at 60 degrees north and 10 hectopascals. And when we have weak vortex conditions, we have a really reduced westerly flow, even to the point where it becomes negative or it becomes easterly when we have events like sudden stratospheric warmings. So the pathway to get this disturbed vortex, where we can have this really high meridional flow pathway, has been, the subject of research for a long time, and we've identified specific things that happen to get these weak vortex conditions. And then once we have these weak vortex conditions, there's a pathway for them to impact the troposphere. And that's what's really represented in this figure. And so if you look at this figure is a schematic of these processes. And if we start on the left side at time number 1 here, we have anomalous sources of wave activity in the troposphere. So all of this starts in the troposphere. We have wave amplification. The waves propagate vertically, and we can capture this with wave activity flux that's directed upwards. And then eventually that wave activity flux converges in the stratosphere, produces our distorted or disrupted polar vortex. And then once we have this disrupted polar vortex, this is really where we get that predictability on the subseasonal timescales that allows us to think about what might happen in the troposphere. So the upward component is really our skill is currently on the synoptic timescales, but the downward component is where we gain our skill on the subseasonal timescales. So from the downward component, we have weakened vortex conditions. We have a downward directed momentum and thermal anomalies that can manifest as negative NAM or AO conditions, Arctic oscillation conditions that can reach the tropopause and impact weather in the troposphere. So if we're thinking about this and we're thinking about using the stratosphere to actually make forecasts for tropospheric extremes, the changes in the strength and location of that stratospheric vortex can serve as a source of predictability on the troposphere. And we know that there's specific conditions that can lead to surface impacts, including really extreme cold temperatures, including cold air outbreaks. And so some of the strongest connections between the cold air outbreaks in stratospheric variability occur in Eurasia, but there's also a signal, a weaker signal, but still a signal in North America. So a lot of times, Eastern Canada becomes warm after these events, but there's a signal for sometimes cold in North America. And so it's these things that we're really trying to understand in our work. So we mentioned that we can think about the strength of the polar vortex, that westerly flow, as thinking about it from a zonal mean perspective, where we're thinking about the zonal mean winds at 60 degrees north and 10 hectopascals as a metric for determining the vortex strength. But I also mentioned that the vortex can get distorted or elongated. And so this is a component that we're particularly interested in exploring on whether or not the elongation or the shape of the vortex gives us any additional information about the subseasonal source of predictability. And so the shape of the stratospheric polar vortex can also be an indicator of stratospheric impacts. And there's been a number of studies that have talked about how the elongation of the vortex can be a signal for North American cold. And so in this diagram, what you're looking at is the 10 hectopascal geopotential height in white and the potential vorticity in the color fill. But you'll notice that there's also a representative ellipse. And so this is really where Elena's work comes in, is we've found a way that we can easily quantify the shape of the polar vortex using what we call ellipse diagnostics. So we fit an ellipse to the shape of the polar vortex, and then we use the characteristics of that ellipse to think about potential impacts. And so this is where I'm going to hand it over to Elena so that she can discuss her work thinking about this from a machine learning and AI perspective.
Okay, great. Thank you, Andrea. So we can just go to the next slide. So kind of as already was addressed, I'm focusing on how we can use these features from the shape of the stratospheric polar vortex to kind of create forecasts downward into the troposphere with the overall goal of somehow improving our understanding or creation of subseasonal forecasts. So within the work, this current little research project that I'm doing, I asked the following questions as to whether or not it's possible to use the shape of the stratospheric polar vortex or these ellipse metrics for predicting temperature extremes in the northern hemisphere. And then the secondary question is whether these ellipse metrics can be used in identifying forecasts of opportunity for these outcomes. And specifically for when I'm talking about forecasts of opportunity, I'm referring to identifying instances of heightened predictive skill that can be leveraged in informing forecasts from these stratospheric features. Okay, next slide. The specific method that I used in this case was building a set of random forest models. So I had one that was used primarily for feature selection, and the second I used for reducing the model and evaluating the results with explainable AI. So both random forest models were tasked with predicting the classification of the 14-day lag temperature anomalies over a region of interest, and I specifically looked at that Eurasia region that Andrea had shown in that Butler figure. And I ultimately also ended up doing some hyperparameter tuning for these random forest models and used the same architecture for both. When discussing the results here, both models were cross-validated 100 instances, with the first 57 years of the data set that I used were training, and the remaining 5 years were used for testing. And then from within that testing data set, I would randomly select a 5 years, set of 5 years as the validation data. I specifically used ERA5 wintertime data in the Northern Hemisphere between November and March from the years listed. And then for my random forest model, the 8 input features were a mixture of daily anomalies for variables with known connections to stratospheric variability, in addition to the ellipse metrics mentioned previously. So just to list them off, I had the daily anomalies for polar cap potential vorticity at 100 hectopascals, so a lower stratospheric level. North Atlantic geopotential height anomalies at 500 hectopascals, just to kind of capture an AO signal. And then the zonal mean zonal wind, and then the 5 additional calculated stratospheric polar vortex ellipse metrics at 50 hectopascals. And then the target output of the model was classifying these temperature anomalies in that region of Eurasia with known temperature sensitivity to vortex behavior as either a positive temperature anomaly outcome or a negative temperature anomaly outcome. So just whether or not it was greater than or less than 0. Okay, next slide. So as Andrea kind of already alluded to, the process of how these are calculated, but essentially what we did is used a best fit ellipse methodology in fitting an ellipse to a desired contour of geopotential height in the stratosphere. In this case, looking at 50 hectopascals, this would be the 20-kilometer contour of geopotential height, and then this can be done at other levels depending on your area of interest. And then once you have that best fit ellipse, you're able to take geometric quantities of it through time, and these are listed here on the left. So what we had were the center latitude and longitude location of the ellipse relative to the pole, the long axis and short axis, and then the ratio between the two, the overall vortex area or its extent, and then the last was the vortex angle, so how tilted it was away from the 0 degrees longitude. These are not spatial values. They're one-dimensional time series values. So I did the same for the zonal mean wind that was used, as well as geopotential height and PV. And just as a quick note, we do have a repository that will be submitted for peer review with a paper soon that would contain the code for calculating these if you were interested in playing around with them for yourself. Okay, so next slide, please. Into some results. This is from the first model, which had all 8 input features used. The goal here was kind of just to see which of those were most important for the model's decision making from that first random forest model, which had an overall accuracy of around 62% for the 100 cross validations on the training data set, which is not great when you consider that random guessing is 50%. I'll add that I did calculate additional statistical scores for assessing the model's performance, but I kind of left them out here for the sake of time. And they more or less tell the same story, which is just a meh performance on the part of the model, excuse me. And then from this figure on the left, we can easily see that for these predictions of the lagged temperature anomalies, the most important feature overall for this model was identified as the actual size or the extent of the vortex, so how large or small the vortex is itself. Then it's followed thereafter by the central longitude, so how easterly or westerly located the ellipse is, as well as the zonal mean wind speed, so defining the actual strength of a vortex. So overall, the message we're able to receive from these top 3 features is that the vortex's extent, location, and overall strength were most crucial to how the model ultimately made its decisions. Next slide, please. And then moving on to the next one, I could have used all 8 input features for this, and I did test it with them, but elected to show the outcomes here using only the 3 most important features. This was kind of also done to compare the results of this with the full model. And overwhelmingly, what I noticed is that it made no difference to the model's performance if I excluded those other 5 features. So the average accuracy of this model was still near like 61, 62%. So it really wasn't much of a change at all. I used an XAI technique to evaluate the results from this model, so SHAP, to look at the importance and sign of the input features for the model's decision making, and used rankings to compare consistency with the previous model. And I have those separated on the right there by the sign of temperature class being predicted. So positive is on the top, and negative is on the bottom. And ultimately, what you can kind of observe is that the features are in the same order of importance for size, central longitude, and wind, and that's consistent with the previous model. But more importantly, you can kind of look for physical signs of significance in the model's decision making through the signs of importance of features relative to the temperature outcomes. So for example, just kind of tying back to that Butler figure from earlier, if you look at the bottom panel, the SHAP panel, in the case of the weakened polar vortex, and if we're expecting a negative temperature outcome, you look at the zonal mean winds, which is that bottom figure, and you're able to see there's a slightly negative preference for zonal mean wind speeds, as well as a preference for more positive ellipse sizes. So kind of being physically consistent for what we might expect for a given outcome. I guess, Andrea, you can click for the little blurb I had at the bottom there. Yeah, so overall we see that these are not a skit of skillful models by any means, which effectively answers the first research question of whether or not it's possible to use these for creating predictions. So the answer is no. However, there's still potentially some promising physical information that we're seeing from these results. So that kind of starts to approach this next question of whether or not we can use these for pinpointing forecasts of opportunity. So for this next step, what I kind of did is mirrored a methodology for identifying forecasts of opportunity from a paper by Mayer and Barnes in 2021. Next slide, please. And what's important to consider is that when looking for forecasts of opportunity, it's not necessary actually to analyze a model with high overall accuracy. What's actually more important from that model itself is whether or not the accuracy of those most confident predictions is higher, kind of indicating these instances of increased or heightened predictive skill. So when you conduct cross-validations on the model, you look at the average accuracy across all predictions made in the model on the testing data set, and then compare those with the accuracies of those higher confidence predictions. So for example, let's say on one day you have probabilities of classifying in each category that are 40 and 60, and that's kind of your average. But then on the next day, where there's increased confidence, the probabilities are 20 and 80. So you're more confident that that day is going to have a warm anomaly. So for each cross-validation, you go through and save the average overall accuracies and then the average accuracies of those selected higher confidence days, and then plot their distribution, which is what I did on the right. And as I've kind of already said, if that distribution for those higher confidence events is greater on average, this indicates some potential for identifying forecasts of opportunity from within those selected events, with the motivation being that something is happening there that's making the model more confident. Next slide, please. So just to look a little bit more at this figure, the dark blue bar is the average accuracy, and the light blue are those most confident predictions. And in those higher confidence days, the model is performing with a slightly greater accuracy, closer to like 75-ish%, which is slightly higher than the overall accuracy of the model, which was closer to 60. So, and then this little table that I attached here at the bottom shows the specific percentages of correctly and incorrectly labeled events from within these higher confidence days. So we're able to see kind of whether or not the model has a preference towards labeling things as positive or negative. And overall, what we can see here is that by proportion, the model performs slightly better at predicting positive temperature anomalies. Next slide, please. I then went a little further and kind of like isolated the individual high confidence events from each cross-validation on the testing data, and then evaluated the distribution of the predictors relative to the sign of the expected temperature anomaly. Excuse me. And this provides some kind of further insight into the model's decision making during these specific events, and allows us to kind of make physical observations about the vortex behavior as well. And what we're immediately able to see is how the model may have gotten confused in classification just purely by looking at overlaps and distributions across these different features. So Most notably, if you look at those middle two bar plots, which are correct negative and incorrectly labeled negative and incorrectly labeled negative, it's a little small on my screen, so I can't read. But if you look at those middle two bars across all panels, you're able to see how close those two distributions are, so you can understand how the model might have taken a positive event from those instances and labeled it as negative incorrectly just by comparing the two. Next slide, please. And additionally, we're also able to use these to see that the distributions kind of reflect the signs of importance that I'd shown in the SHAP plots previously. So there is some physical consistency going on here. Just to point out some specific similarities, if you look at those far leftmost with box plots, you're able to see that higher zonal mean wind speed distribution, eastward central longitude location, and a smaller on average vortex size, which would correspond to that correct positive classification or a strong vortex event. So just to kind of summarize, there's some physical evidence here to support that these metrics may be useful in identifying forecasts of opportunity for connecting stratospheric behavior with S2S forecasts of surface temperature anomalies. It would just ultimately be a matter of extracting that specific information for features preceding extremes and using that to inform decision making. Next slide, please. So just to restate takeaways from this analysis, the stratospheric polar vortex ellipse metrics that we're talking about are not actually overly useful for creating confident predictions of northern hemisphere temperature anomalies, but they do provide some potential use for identifying windows of opportunity on the S2S scale and can be used or may be used for connecting stratospheric behavior to tropospheric outcomes in that way. But from here, I am looking to move on from using these ellipse metrics as the core of my work, and instead I'm going to be looking for other ways to capture these cross-tropopause interactions from the stratosphere downward and create more physically reliable subseasonal scale predictions using AI and machine learning toolkits. And next slide, please. One of the ways that I'm thinking about approaching this, and I've already started to do so, is through using EOF and principal component analysis on a few different atmospheric features to capture various types of stratospheric variability. Examples of these are shown on the right and include kind of these vertical cross sections of wave activity flux to represent changes upward and downward to the stratospheric circulation across the tropopause. So from these cross EOF analysis, I'll select principal components from these through sequential feature selection, and then use those PCs as predictors for a machine learning model that will ideally somehow capture these cross-tropopause interactions between the wintertime stratosphere downwards into the troposphere. And currently my plan is to use a long short-term memory model or an LSTM model, and then add in an attention layer as a fun little bit to see which of the time steps on the S2S scale is actually most important for the decision making in this case. So I think this approach might provide a more complete view of the upward and downward interactions across the tropopause. So yeah, otherwise that's what we've been working on, and we'll take any questions.
Thank you so much, both Andrea and Elena. That was great. I'll wait for participants to ask some questions, and we've got a couple coming in. One question is, would it be useful to extend to 1 month lead time?
So I'll kick off the answer to that question by saying we did look at a variety of different timescales. We used the 14 days as sort of a proof of concept, if you will. So Elena in her future work is now looking at using time series data to really get at looking at, what is the variability in a window, a subseasonal window look like.
Yeah, for the specific models that I was doing, I chose a set of different days. I went out as far as 25 and then as short as 10, and then more or less just kind of assessed the differences in model performance and sat with the middle result, which was 14 presented here. So
Thank you. We have another comment leading into a question. So the stratospheric polar vortex ellipse metrics that you're using are indeed good physical proxies for stratospheric variability that can link polar vortex to northern hemisphere mid-latitude surface temperature anomaly. This person thinks the teleconnection indices you mentioned, such as the NAO and AO, could represent tropospheric response of polar vortex changes. And wonders if AI or machine learning can be used to identify such connections or simulate surface temperature. Do you have any thoughts on that?
I can provide, yeah. So I had done a little side project prior to AGU that I had presented on that was kind of looking at doing that, or I specifically focused on trying to do this joint model where I was using it's kind of like the first step of the machine learning model, or it was like I did a primary ANN that was assessing stratospheric vortex shape and then connecting that downwards to the NAO and then connecting the NAO response to temperature outcomes in specific regions. And the issues I was having with that is that one, it was hard to evaluate the physical decision making of that model because it had a really complicated architecture. But then second to that is that what I was able to evaluate from it, at least on the very short time scale that I was looking at it, was that the model was placing preference on the synoptic scale features from the geopotential height representing the NAO rather than focusing so much on the stratospheric component. So I think it'd be worthwhile to circle back to that. It's just not something that I'd be focusing on doing currently.
Yeah. And I'm going to add a two more. So going back to this figure. So there's been some work that's looked at specifically North American cold air outbreaks and temperature outcomes from stratospheric variability. And the AO is not necessarily the strongest signal for those particular outcomes from stratospheric variability to cold over North America. So it's possible to include the AO, but there's also things like stratospheric wave reflection events that have more of a signal in the Pacific. So trying to capture that variability in the metrics we're using is something we're still working on. And we're hoping that these EOFs, in that perspective, looking at this vertical cross-section space, will really resolve the variability that maybe doesn't project onto the AO and AO as well.
Thank you both. For the sake of time, we're going to move on to our next presentation, but I encourage participants, if you have more questions for Andrea and Elena, to keep sending them in and I'll pass them along. And now I'm changing the presenter to Cameron. So our next presenters will be Cameron Lee, an associate professor in geography at Kent State University, presenting with postdoctoral researcher Chibuike Ibabuchi. As part of their research, Cameron and Chibuike developed a project supported by the Climate Program Office's Modeling, Analysis, Predictions, and Projections, or MAP program, focusing on excess heat and excess cold factors, working toward establishing a unified duration intensity metric for monitoring hazardous temperature conditions in North America. So we're excited to hear about your work. Thank you, and go ahead.
Great. Yeah, thanks a lot for the introduction, and thank you guys all for joining us. Yeah, I'm Cameron Lee, Associate Professor at Kent State University. This is Chibuike Ibabuchi. He is a postdoc in my lab. I just wanted to kind of introduce some of the different work, not knowing everything about the audience here, kind of introduce some of the different work that we do in the lab before we get into the specific project of that you guys came here to listen to. The climate research in our lab, and specifically the climate and AI research in our lab, takes on a synoptic climatological focus. In fact, the lab ClimeRise stands for Climate Research in Synoptic Environments. That's how we came up with this acronym. And so we do definitely have a focus on synoptic features of the atmosphere. Not only the time and space scale that we regularly define synoptic, but also those features that are firmly within that synoptic perspective. So looking at troughs and ridges, highs and lows, cyclonic flow versus anticyclonic flow, air masses, frontal boundaries, and just general patterns of atmospheric circulation. We are firmly focused on a lot of these features of the atmosphere and then incorporating them into various AI models in order to look into a variety of different applications. Some of the applications that we have looked at, you can see on this slide. Some of our recent research has looked at synoptic climatology and tornadic activity using an AI-based classification known as self-organizing maps to define atmospheric circulation and then use those patterns as input into artificial neural networks in order to evaluate and learn the relationship between synoptic patterns and tornadic activity and project them into the future. We've done similar things with sea level, looking at these larger synoptic scale circulation patterns and seeing how they affect day-to-day sea level variability, how they affect the risk of nuisance flooding / sunny day flooding, and found a fairly significant relationships. Another key way in which a lot of our research has been useful is in analyzing human health, especially human mortality, as it's a pretty tricky, kind of a tricky relationship to tease out, and this is where a lot of like artificial neural network based modeling comes into play. You have acclimatization of a population, you have seasonality in terms of the effects of heat in winter versus the effects of heat in summer. You have lag time involved in terms of when some type of weather event happens versus when it has an effect on the people. And then there's multiple impactful variables. It's not just temperature, but it's also humidity. It's also radiation / a lack of radiation. It's also wind speed. And so taking all of those things into consideration, it lends well to using highly flexible models such as artificial neural network models. There's a variety of other applications in synoptic climatology and AI that we do in our lab, but our latest research is funded, as was mentioned earlier, by the NOAA's Climate Program Office, entitled Excess Heat and Excess Cold Factors, establishing a unified duration intensity metric for monitoring hazardous temperature conditions in North America. The goal here being establishing, again, a unified across all of the United States duration and intensity metric. It's not just the magnitude of temperature, but also how long it lasts that often is most impactful to the general population. So with that, I am going to turn it over to my postdoc, Chibuki Ibebuchi, in order to talk about a few different aspects of this particular research project that we've published on recently. Chibuki?
So thank you for introducing me. So first of all, we use AI to select the best reanalysis data set that represents station observations so that we can have some confidence in our results. And that is the first aspect of our research that I'll be presenting. So this research has also been published at JGR, Machine Learning and Computation. It generally looked at different reanalysis products and used AI to evaluate which performs best in representing station-based apparent temperature. So first, we benefited from the strength of reanalysis data sets as they provide a wide range of spatio-temporally complete climate variables across the globe. But however, being products of data assimilation, we also know that they are subject to biases. So their applicability to climate impact research should be with caution. So we use AI to post-process the reanalysis data sets to adjust some of the biases and also to decide which performs best in representing observational data. So we looked at different reanalysis data sets at their common availability period, which is from 1980 to 2015, and the reference data set, which is the station data, was obtained from the Integrated Surface Database, that is ISD. And the different reanalysis data sets that we use for this research includes ERA5, which has the highest resolution, the MERA2 20th Century Reanalysis version 3, and the North American Regional Reanalysis. So we selected those ISD stations that have at least 95.5% of complete data, and we can see their spatial distribution across the contiguous United States. So the goal is to compare the reanalysis data set to these station-based data sets to evaluate their performance. Now, we use the feed-forward neural network for this study, and the reason why we chose this model is because we consider that the relationship between the predictor and the predictant, that the predictor in this case is the reanalysis data set, whereas the predictor is the station data, that they are mostly linear. So the feed-forward neural network was sufficient for our study, so we did not use the long short-term memory or transformer or other advanced neural network models. So this was sufficient for the task at hand. And our model included inputting the reanalysis data set and the station data set, and the hidden layer is designed to adjust the weights of the two data sets in order to adjust the biases in the reanalysis so they are close as possible to station observations, and the output is the post-processed reanalysis data set with most of the systematic biases expected to be adjusted. So we did our hyperparameter tuning objectively using the Keras tuner, and we selected the optimal hyperparameters to ensure that our model is as optimal as possible. So first, we did a diagnostic check whereby we looked at the correlations between daily apparent temperature. But by apparent temperature, I mean that we're not just using the ambient 2-meter temperature, but we also incorporate humidity and wind speed so that we can have a holistic view of how temperature impacts the biologic environment. So by looking at the correlation between the assimilated temperature from the reanalysis data set and observations, we can see high correlations, especially at the eastern parts of the US. But when we start going towards the western parts, especially at the coastal regions, the correlation starts to decrease. And the reason for this is mostly because of the sparsity of data in the western part of the US and also the complex topography. And generally, the ERA5 has the highest correlations, followed by MERA2 now, while the 20th century reanalysis performs least. And what this tells us is also that there is the room to adjust some of the biases using artificial neural network models in order to improve the performance of the reanalysis data set in representing station observations. So here we look at the distribution of the errors, that's the mean absolute error and the root mean square error for the raw reanalysis data set and also for the post-processed reanalysis data set. And interestingly, we can see that the errors reduced significantly for the post-processed reanalysis data set, and most of the errors in the western part of the US were well adjusted so that the data set becomes closer to observations. And this was consistent across all the reanalysis data sets, both for the mean absolute error and for the root mean square errors. So next, to evaluate and know which data set performs best in capturing the observed reanalysis data, we also checked their ability to predict the station-based data, and then we looked at the errors, and we can see from the distribution of the errors that ERA5 performed best with the lowest error in predicting the station-based observational data set. So this gives us confidence that for our further research, that ERA5 is relatively the most accurate. So we will be focusing more on the results from it compared to that from other reanalysis data sets. So this is the basic application of AI in our research, which is in post-processing our data set and also knowing the data set that performs best in representing station observations. So the conclusions from our first research is that the reanalysis dataset they captured daily variability of apparent temperature in the eastern regions of the United States compared to the western coastal regions. And also by post-processing the reanalysis dataset using AI, most of the biases were adjusted relative to station observations. And generally, ERA5 performed best in representing the station-based apparent temperature across the contiguous United States. So this leads us to our next research, whereby we looked at the recent trends in extreme temperature events across the contiguous United States. And this research also has been published in the International Journal of Climatology. Generally, we looked at these trends in extreme temperature events using the evaluated reanalysis data sets in order to see the spatiotemporal structure of these events and also their trends over time. So the study objective generally is to assess the trends in extreme temperature events and also to compare the trends across the three reanalysis data sets, including ERA5, NA, and MERA2. So we define extreme temperature events. First of all, we define the excess temperature factors, which is a duration intensity metric that is based on the exceedance of apparent temperature beyond local percentile thresholds. And we also incorporated acclimatization factor in order to capture local adaptations to temperature extremes. Then from the excess temperature factors, we define the absolute extreme heat events, which is the exceedance of extreme heat factors above the local 85th percentile threshold. This metric is designed to capture extreme events that occur typically during the warm months, that's the summer months. And we also have the extreme cold events, which looks at exceedance of extreme cold factors above the local 15th percentile threshold. And the metric is designed to capture extreme cold events that are typical in cold months or say the winter months. We also have the seasonally relative events, whereby we looked at the relative extreme heat events and relative extreme cold events. For the relative extreme heat event is the exceedance of the seasonally relative extreme heat factors above the local 85 percentile threshold, and this metric is designed to capture extreme heat events that are relative to the expected seasonal norm, so they can occur outside the typical warm months. And also the same for the extreme cold events, which can occur outside the typical cold months. So even in winter, we can have the possibility of relative extreme heat events and such like that. So here shows our results on looking at the trends in these events across the contiguous United States, and we can see that the extreme heat events that they have positive trend, which is fairly consistent across the reanalysis data sets in the western and the southwestern parts of the contiguous United States, whereas the relative extreme heat events also have statistically significant positive trends in the southern parts of the United States, and this is fairly consistent across the reanalysis data sets. And we are also focusing more on ERA5 because our fourth study shows that this is the most consistent in capturing observations. For extreme cold events, the trends were more sparse, but for the relative extreme cold events, we can also see that they are significantly decreasing at the western and the eastern coasts of the United States. So for the spatially averaged events, we found a positive trend in extreme heat events and relative extreme heat events, and a negative trend in extreme cold events and relative cold events. And interestingly, we also found that the rate of decrease in cold events is relatively greater when compared to the rate of decrease in extreme heat events. So this brings us to the conclusion of our second study, which shows that the frequency of extreme heat events is significantly increasing in the western part of the US, with the highest increase occurring in southern California and Nevada, whereas for the relative extreme heat events, they are also increasing in the southern parts, with the highest increase maxima in Florida. And then the relative extreme cold events are significantly decreasing in spatial scale and magnitude more than the extreme cold events, especially in the coastal regions. And the highest decrease is occurring in Florida Peninsula, Southern California, and Nevada. So this leads us to the third part of our study, which is the risk assessment of counties in the United States that are impacted by frequent hazardous temperature in the contiguous United States. So this aspect of our study is more policy relevant to translate our study into practical use for policymakers. So the study objective is to generally identify the counties in the United States that are impacted by frequent extreme temperature events and identify also the populations that are exposed to frequent extreme temperature events. That's the exposure aspect of our risk assessment, whereas the vulnerability aspect, we looked at the counties that have dominant urban population versus dominant rural populations, and we inferred that those that have dominant urban population, they are less vulnerable compared to those that have dominant rural populations. And we also analyzed the trends in demographic exposure over time to extreme temperature events, and we also compared our results from the three analysis data sets, while also focusing more on ERA 5, since our first research using AI has shown that it's the best performing data. So here we can see the exposed and the non-exposed counties to increasing hazardous temperatures in the United States based on the trend analysis that we did from our former research for the relative extreme heat events and the extreme heat events. And interestingly, looking at this table that shows impacted counties and counties equivalent across the 48 states and the District of Columbia, we found that for extreme heat events, for the 3,109 counties, about 20% are impacted. That's focusing on ERA 5, whereas for the relative extreme heat event, about 37.3% of the counties were exposed to more frequent relative extreme heat events. So we also looked at the percentage of dominant populations in these impacted counties, that is rural versus urban, and we can see some spatial heterogeneity. For example, in the western part, say California, the exposed populations are mostly urban and the same as Florida, but for other places like Texas, the exposed population are mostly rural. Next, we look at the demographic exposure to changes in extreme heat over time. So this was calculated by multiplying the county population based on the 2020 census with the annual occurrence of events, and then we look at the trend over time. The trends were mostly positive, but we can see that areas like Los Angeles in California and other parts of Southern California, other counties in Southern California, that they have higher demographic exposure over time due to both increase in population over this region and also increase in heat events. So we look next at also the population sum of the trends in the exposed counties over time, and we can see that between 1980 and the 2020 census, that we have 46 million exposed, but based on the 2020 census, we now have 92 million people that are exposed, which shows a significant growth, about 100% increase in the exposed population to extreme heat events. Also, for the relative extreme heat events, we also see a similar trend whereby we have currently, based on the 2020 census, about 139 million people in the US that are exposed to relative extreme heat events, and this has grown over time with about 90% increase when compared to the 1980 population census. So the main findings from our results so far is that out of the 3,109 counties and county equivalents analyzed, that 20% were exposed to extreme heat and 37.3% relative extreme heat, and approximately 92 million people are exposed to extreme heat events and 139 million people to relative extreme heat events. And between 1980 to 2020, the total population exposed to extreme heat events and relative extreme heat events has increased by 100%, and exposure to changes in extreme heat events over time was most prominent in urban heavy counties such as Los Angeles and California. And we also created an interactive map that we used to compare our results to both scientists and non-scientists alike, so that when you click a particular county, you can see both the county name, the state that it's in, the trend, the risk score, the dominant population, and also the exposed population, so that both scientists and non-scientists can be able to use our results for practical policy making. So from here, I will hand over to Tom.
Yep. Thanks, Ted. You guys have any questions? We'd be happy to have that conversation.
Thank you so much for that great presentation. I'll wait for some questions to trickle in from participants. I guess a question we can start off with is I'm curious just where you got your county data from and where that data was sourced.
Yeah, that's the U.S. Bureau, the Census Bureau.
The U.S. Census Bureau?
The U.S. Census Bureau, yeah.
On a county by county basis?
Yes.
Great, thank you. So participants, feel free. We're getting some clapping emojis for the presentation, so thank you. And we'll wait just a minute for people to form their questions and put them in the question feature. We have a question. Did you look at ERA5 land, which has a higher resolution compared to ERA5?
No, we used the normal ERA5.
In some prior research that we've done, we've looked at ERA5 land, and in some regards, it was, well, actually, in a lot of regards, it was actually a little bit worse than ERA5, not land. And I think it has something to do with the differences between the way that they assimilate actual observed data between the two data sets.
Great, thank you. I'll wait a minute for any other questions to trickle in. Here we go. Were there any other biometeorological metrics examined? For example, wet bulb temperature or heat index? And were the AI models sensitive to that index?
So we did not look specifically at either one of those. I will say that apparent temperature and heat index aren't all that much different, and apparent temperature takes into consideration more than just the temperature and humidity. It also takes into consideration the wind speed as well. As far as the wet bulb temperature, or the wet bulb globe temperature, no, we didn't specifically look at that one, so can't really comment as on whether or not they were significantly different than what we presented here.
Okay, great. If you do have any other questions, feel free to send them in and I can pass them along. I'm putting some resources into the chat to learn more about us and our past and future webinars. The link that I just put in the chat is where the recording of this webinar will appear in the coming days. And I'll just share my screen. So thank you all again for joining us, and thanks to all our presenters for sharing your work and to the participants for asking great questions. The Climate Program Office and the NOAA Center for AI is excited to host more of these webinars in this series. So our next webinar is going to be on May 9th. The speakers will focus on AI as a tool in studying ocean and coastal science. We'll be sharing registration information on this upcoming webinar later this week. So as I said, there's some resources in the chat for learning more about the NOAA Climate Program Office and the NOAA Center for AI. You can also feel free to reach out directly to me with any questions about CPO or NCAI or this webinar series. And again, I'm happy to pass along any other questions for our presenters today. So thank you so much, and thanks for joining us, and we hope to see you next time.
All right, thank you.
Thanks.